Welcome to lecture over 2.1 sets and sets operation. So we're going to talk about the basic vocabulary and the notation of set theory. So this is a branch of mathematics which is beneficial when we talk about probability and also beneficial when you get to statistics. We won't go too in detail about it, so we just kind of skim the surface. We'll learn how to apply unions, intersections, and the complement operation. So we're going to talk about the union of sets, the intersection of sets, and then we'll also talk about complements operation. And then we're going to draw Venn diagrams to kind of see a picture of what goes on. This is going to be very similar to the conjunction and disjunction when we talked about logic. So grouping two things using the word or, grouping two things using the word and. So that's going to come up again, and you'll see similarities with logic and sets. So the first thing we talk about is a set is just a collection of objects or things. The objects or things are called elements or members of the set. So notation, there's really two common notations used when we're talking about sets, and we can use the roster notation. The roster notation is called the listing notation. I'm going to list all my elements in between these set braces. So an example of that I give here is let R be the set of the letters in the word Stephanie. So there are 8 letters in the word Stephanie. We use an S, a T, an E, a P, an H, an A, an N, and an I. So one thing we notice is we don't list elements more than once. So these 8 letters make up the word Stephanie. A little bit more on notation. For example here, P is an element of the set, I'm going to write that with this symbol, this sideways looking E, or this weird looking E. That means an element of. The E with a slash through it means not an element of. So that's things to keep. When we get to the WebAssign, they'll have something like, is P an element of R? And you would say true or false. So being able to read this and understand what it means, the notation of it means. So P is an element of R. X is not in the set R. X is not one of the letters that make up the word Stephanie. So you would write X is not an element of R. And here we have the notation, this N, comma R, is notated for the size. So more specifically, how many elements? So number of elements. Okay. So the next type of notation that's possible to see is this set builder notation. Set builder notation comes in handy when your sets are infinitely long. So that means there are infinite number of elements in the set. This example here is given on your PowerPoint, and it's saying we're going to name the set G. Set G such that all X such that X is less than 0 and X is a real number. So this line in the set notation, set builder notation, is read as such that. So we have X such that X is less than 0 and X is a real number. So this is the notation for a real number. So if I was to list the elements in G, it might look like negative 100, negative 50, negative 99, etc. There's infinite elements in this set. So set builder notation is really a better way to write it than listing out all the elements, because it's impossible to list out all the elements. So one other comment is an empty set. Eventually we'll talk about the intersection of two sets. So if I have the intersection of 1, 2, 3, the set 1, 2, 3, and the intersection of a set 5, 6, 7, they don't have any elements in common. So the way that we write that, the intersection is still going to be a set, but we denote it by this 0 with a slash through it. Or in set notation, or in bracket notation, we would just have empty brackets. So what this means is the intersection's a set, but it's the empty set. So that's something to keep in mind when we get to the homework. The next thing we'll talk about is universal sets and subsets. So in any given problem, you're going to have a universal set. And what that means is it's the set of all possible elements used in the problem. So an example would be if you're spelling words, the universe is going to be all the letters in the alphabet. So I could list them A, B, C, D, E, F, G, all the way through Z. So the size of the set is 26. So the number of elements in U would be 26. Now I might look at the subset being the elements that spell pen. So I could say something like A is a set of letters in pen. So P is in there, I is in there, and N is in there. B being the elements that make up the word pine. So this brings us to subset. So I could say A is a subset of B. And I can denote that as A and then the symbol subset of B. What that means, every element in A is also in B. So graphically, we can show it with a Venn diagram. So this would represent A is a subset of B. Every element in A is also in B. We have things called proper subset and improper subset. A proper subset just means that A is smaller than B, and that's going to come up in the examples we talk about later on. If I say a proper subset, that means A is smaller than B. But if the sets were the same, A and B, if A equaled B, then that would just be an improper subset, and that will come up in WebAssign. And this is also on your PowerPoint with proper and improper. So intersection of sets, this is going to be very similar to our conjunction where we use the word and. So the intersection would be represented as A intersection B. So when you've seen this symbol, you understand that's A intersection B. So we join it with the word and. So what this means is the elements in A and in B, where they overlap. So if I look at the Venn diagram, and this is figure 2.2 in your book, and I didn't copy it from the PowerPoint, but you can see that, and it's pretty straightforward. If I have the universal set, this is the universe, and I have a set A and a set B, so this is set A and this is set B, then the middle here is going to be the intersection. So, sorry, this is not right. It's not the middle, it's the whole thing. The whole thing. This is in A and in B. Sorry, I'm getting ahead of myself. Okay, so forget what I just said. I'm looking for the intersection, and the intersection is going to be what I originally said. It's in A and in B at the same time. So this is A intersection B. So both the elements that they have in common. So sometimes using the word and can be a little confusing because you think A and B, but it's the elements in A and the elements that are also in A that are also in B. So I tend to try to use the word common when I'm looking at the intersection. So let's look at a quick example here. This example is in your PowerPoint. We have a list of names. So we have the list A and the list of B. Their intersection would be denoted as A intersection B. So half the battle in this chapter is knowing the notation, what this means. When you say A, when you see this A, this symbol B, that just means the intersection, the elements they have in common, and you see that they have two elements in common, Buffy and Spike. So the next thing we'll talk about is mutually exclusive. Sometimes it's possible that we have no elements in common. There's no overlap. So this example here, D is the set that has of cards where the cards are diamonds. So we have the 2 of diamonds, the 3 of diamonds, the 4 of diamonds, the 5 of diamonds, all the way up to the ace of diamonds. And S is the set of cards that are spades. So we have the 2 of spades, the 3 of spades, so forth. Now, certainly it's clear that no cards are both diamonds and spades at the same time. So what that means is that the intersection is the empty set. So remember, this is the empty set. Empty set. So you wouldn't write 0, because if you wrote 0, that would say that the intersection is the card 0, and that doesn't make sense. So you mean this 0 with a slash through it, meaning the empty set, no elements in common. When the intersection is the empty set, we say that they're mutually exclusive or disjoined. So graphically, we have this mutually exclusive set, no elements in common, so we would write that as the intersection is the empty set. They don't have any overlapping. All the elements in A is just in A, all the elements in B are just in B, and there's no overlapping. Then it brings us to the union of sets, and we can think about this as joining A and B with the word or. So you can see this or here. So it's all the elements that are in either A or B. So the representation of the union, and I always like to remember as union starts with U. So I have A, U, B, that's the union, and that's going to be everything in A, including everything in B. So it's this whole area. On WebAssign, there will be little check mark boxes, and you'll have to check the boxes that represent the union of possibly A, union, and B. So you would check everything in A, everything in B, and then also that includes everything in A and B. So this example given, Conan, David is in A, Ellen, Kate, and Oprah is in B. Their union, so remember union would be both. So union is in both Conan, David, Ellen, Kate, and Oprah. So you list all the elements in A and all the elements in B. Their intersection, this is the one that's in A and B. So the ones that are in A and B at the same time. And that would be the empty set again. So they have no elements in common. So they're mutually exclusive. So let's look at some examples here. Given this set, A is 1, 2, 3, and B is 2, 4, 6, find the following. Find the intersection, A intersection B. Now, remember, you won't be given this explanation on WebAssign and on a quiz or on an exam. You need to know that A, this symbol B, means the intersection. So if you recall what the intersection is, so if we go up and we find this formula of intersection, it means the ones they have in common. So if you need to write this down on a note card, you have note card on the exam, so that would be something you want to keep straight. So the elements they have in common, and they have a 2 in common. So you write this bracket notation, and WebAssign gives you the bracket notation, so you would just put in a 2. So the elements they have in common is a 2. If I wanted to go ahead and see if it comes up later on and look at the union, if I say A union B, that's going to be the elements that are in both. So I like to think of this as in common, and this is that are in both. So I'd list 1, 2, 3, 4, and 6. Note, I don't list 2 twice. So do not list elements more than once. Okay, so moving on. So we get this formula for being able to find the union, the intersection, and the number of elements in A and B. So this is a formula that if I give you 3 of the 4 quantities, so as long as 3 of the 4 quantities are known, you can find the missing quantity by algebraic manipulation. So let's look at doing an example of this. So here, if I'm finding the number of elements in the union, so how many elements are shared with A and B, I take the number of elements in A plus the number of elements in B, and I subtract out the repeats. So these are the union, so all the elements in A plus all the elements in B minus the repeat. So if you notice up here in this example, looking for the union, the number of elements in A is 3. So the number of elements in A would be 3. The number of elements in B would be 3. And then the number of elements in A intersection B was 1. So if I want the union, so if I wanted the A union B, the number of elements in A union B, I take the number of elements in A plus the number of elements in B minus the number of elements in the intersection, A intersection B. So if I'm looking for this quantity, in this example I take 3 plus 3 minus 1, which would give me 6 minus 1, which would give me 5. That tells me there's 5 elements in the union of the sets. And I got that here, 1, 2, 3, 4, 5. So notice I don't list the elements that repeat, and the intersection tells you how many elements are in A common to A and B together. So these are the number of repeats. If I add 3 plus 3, I need to subtract the repeat to get 5. So there's going to be 5 elements in this union of A and B. Okay, so let's look at this example here. This is just another example of it. So you're given the number of elements in A and the number of elements in B. Part A, you're also given the number of elements in the intersection. So if I want to find, if I look at this formula, and I pull this formula down here, I'm going to write that the number of elements in A union B equals the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. So I want to find, I'm asked to find the number of elements in the union. So this quantity is not known. So I put a question mark. That's what I want to find. I know the number of elements in A because that was given in the problem here. I know that's 81. The number of elements in B was given in the problem here. So let's say the number of elements in B were given in the problem, and I know that's 66. And then the number of elements in A intersection B was given here, and that's 47. So now to find the number of elements in A union B, I take 81 plus 66 minus 47, and I get 100. So that tells me there's 100 elements in A union B. So A and B together, there's 100 elements. But if I add these two numbers together, I'm going to have 147. That's because 47 elements are in both A and B. So when I list the union, I won't list the repeats twice. So I need to subtract out 47 when I just take the number of elements in A plus the number of elements B minus 47 gives me 100. So let's look at this next example. Let's take this same formula here. See if I can copy this over. I'll just rewrite it. So I'm taking this same formula. So I'm taking the number of elements in A union B equals the number of elements in A plus the number of elements in B minus the number of elements in the intersection. So I know the number of elements in A was given as 81, and then the number of elements in B is given as 66. In this example, they're asking me to find the number of elements, where did my little mouse go, in A union B. So they're asking me to find this quantity. So this would be minus the question mark, and over here, they're giving me that there's 147 in the union. So I have 147 in the union. So what I want to do is I want to solve for x, or solve for this question. So I would take 147 equals 147 minus question mark, because 81 plus 66 is 147, so that tells me question mark must be 0. So question mark being 0, that means the number of elements in A union B have to be 0. So you wouldn't write the empty set here because this means number of elements. This is number of elements. You would write that A intersection B would be the empty set, meaning there's no elements. So be careful on things like that. And we'll talk about complements of set. So a complement of a set is denoted by A prime, and a lot of times we read it as A naught. So what that means is it's all the elements left in the universe that's not in A. So it's all the elements that are in the universal set but not in the given set. So graphic representation of that would be if I have A prime is everything outside of A. So all this would be A prime. And generally we read it as A naught. So some formulas here. If I know the number of elements in the universe, that's going to be the number of elements in A plus the number of elements in A naught. I can rearrange this formula and solve for the number of elements in A and the number of elements in A naught. So sometimes this is nice because we don't want to think about how many elements are in A, we want to think about how many elements are in A naught. The example your PowerPoint gives is how many letters are in the alphabet preceding the letter W. So the size of the universe is 26. There's 26 letters in the alphabet. Well, A, B, C, D, I could count how many letters are before W, but it would be easier to count how many letters are after W. So we have W, X, Y, and Z. So the size of, let's just call it W naught, because preceding the letter W would be how many letters in the alphabet preceding the letter W. So we wouldn't count W in that. So W, X, Y, and Z would be letters that come after W or that are W. So W, X, Y, and Z. So the size of this is 4. So the number of elements that come before W would be 26 minus 4. So 22. So there's 22 elements, there's 22 letters of the alphabet that precede the letter W. So sometimes thinking in not W makes the work easier to do. Shading Venn diagrams. So this example, if I have A and then remember what this symbol means, this is the intersection and this is the union. So A intersection B naught. So if first off, let's kind of see what's going on here. Let's use blue to be B naught. What is the B naught area? Well, B naught would be everything outside of B. So it's going to be everything in the universe outside of B. So this blue area is going to be B naught. And then A is given here, so this is A. So then if I shade in A, it's everything inside the A circle. Got a little crazy there. Everything inside the A circle. So now I need to determine what this symbol means. This is the intersection. So that means where they overlap. So they overlap in this area here, right? Because I have both blue and yellow highlight in this area. So A intersection with not B would be this area. So on WebAssign, you're going to have a little box to check. You'll have a box here, a box here, a box here, and a box here, and you would just check this box because that would be A intersection B not. This is the union. So doing the same thing, I would shade everything outside of V as blue, and then everything in A, I'm going to shade as yellow. So this would be A. And the union is anything that's shaded is going to be checked. Right? So if you go back up to the definition of union, the union of sets is going to be the boxes are going to be checked if it's in A or if it's in B. So in this example, the box is going to be checked if it's in A or not B. So as far as checking your box, you're going to check anything that's shaded. So this would be checked, this would be checked, and this would be checked. So the only thing not being checked is just B. Set theory and logic are very similar to each other. If you notice, a union is similar to a disjunction, the common word being or. An intersection is similar to a conjunction, the common word being and. A complement is very similar to a negation. If I say not A, the common word being not. So if I say it's snowing, the complement would be it's not snowing. So you would do the same thing with sets. A subset is going to be very similar to a conditional. So that just means if then. If I write something like A is a subset of B, that means if you're an element of A, you're also an element of B. Now, when we talk about unions, intersections, complements, and subsets, you can see how they're written logically. If I say X is an element of the union, that means X is in A or X is in B. Or unions are generally bigger sets. Intersection, if X is an element of the intersection, it means that it's in A and it's in B. If I say X is an element of the complement set of A, that means that this means the not here. So X is an element of the complement means X is not an element of A. And then the subset means if A is a subset of B, you can say if this happens, then X is an element of A implies X is an element of B. If you know this way, you can also work everything backwards. If you know an element is in A or an element's in B, you can say that the element is in the union. An element in A and an element in B, then you would say the element is in the intersection, and so forth. So let's look at some examples. Be careful on your homework this chapter because anything in red will change. So if you do the problem and you get it wrong and you go back to fix something, the red ones will change. On your quiz, the red won't change, but on your homework, you have 6 tries, the red will change. So if the set's empty, you actually enter empty into this set. So here we're looking for A intersection B. So knowing what intersection means, so if we come up here, intersection, it means and. So elements in A and elements in B. So I'm going to list out, I'm not going to have enough room here, but it would be 2, 3, 4, 5, 6. 5 and 6 I don't list again. 7, 8, 9. So be careful not to list repeats. Here I have union, so I have A union B, so those are going to be the elements. If I come back up here, union, it's going to be in the elements OR, so let me pause this real quick. Sorry about that, guys. I switched these examples. So this example here would actually be down here. So let me clear this. So hopefully you learned from my mistakes, and now I look at it here. So A intersection would be the picture of the elements that they have in common. So this is A, and this would be B. This would be A intersection B, where they overlap. So A intersection B in this case is going to be what elements they have in common, and they have a 5 and 6 and a 5 and 6. So that would just be 5, 6. Now union is what I was talking about before. If I look at it graphically, I have A and B. Make it a little bit better. Union is going to be elements in A and elements in B. Or using the word and here is kind of confusing. Here's really where and comes in. Elements in A and also in B at the same time. Here we would use or. List the elements in A would be fine, or the elements in B is fine, so you'd list them all. And that's what we did at first. So A union B is going to be 2, 3, 4, 5, 6, 7, 8, 9. Okay, so sorry about that confusing. If you need to draw these pictures on your note card, that's fine. So you want to make sure you understand what A intersection B means and A union B means. Because if you get them confused, then you might have the right concept by switching them and you won't get the right answer. A complement is going to be all the elements not in A. So 2, 3, 4, 5, and 6, this is the universe. So all the elements left in the universe that's not in A. So 0, 1, because 0 and 1 in the universe, but they're not in A. So 0, 1, 2, 3, 4, 5, 6 are in A, so I won't list them in A not, and then I have 7, 8, 9. B naught is all the elements in the universe that are not in B. So B naught is going to end up being 0, because 0 is not in B, 0, 1, 2, 3, 4, but 5, 6, 7, 8, and 9 are 5, 6, 7, 8, and 9 are in B, so they're not going to be in B naught. So hopefully this makes sense. You have to put commas in between these, so you'd list this as 5, 6. Again, your numbers might be different, so look at that. So this is the example in which I talked about proper subsets and improper subsets. A proper subset is always going to be smaller than the set. So the empty set is always going to be a proper subset. So you have to have empty set in there. So automatically this one's not going to work because it doesn't include the empty set. So if B is Lennon and McCarthy, then the empty set and then having a set of Lennon and having a set of McCarthy separate would be all proper subsets. You can see Lennon and McCarthy is the set, so obviously they're not proper. And then this is Lennon, and because a proper subset is smaller than the set, and this is the same size as the set. So your correct answer here would be the empty set, just Lennon and just McCarthy. The improper subset is going to be the original set, the same size. So same as original set. So here the original set is Lennon and McCarthy, so your answer here, oops, Your answer would be this one. So then if you want to list all possible subsets, then you're going to have the empty set, just a set of Lennon, just a set of McCarthy, and then Lennon and McCarthy together. So 1, 2, 3, 4. There's 4. So the correct answer here would be this one. Because this one doesn't include the whole set. This one doesn't include the set of just Lennon. This one doesn't include the set of just McCarthy. And this one doesn't include the empty set. So your correct answer would be this one. Now, again, remember what the union means. So if I draw that picture, it's going to be everything in A or B. So if I put, let's put just the word or. So I have A not, so everything that's not in A, and then I also list everything that's in B. So first off, I really need to write what A not is. So the universe is the days of the week. A is Monday, Tuesday, Wednesday, Thursday, Friday. So A not would be Sunday and Saturday. So Sunday and Saturday is A not, and then B is also given here as Friday, Saturday, Sunday. So now I'm going to find A not or in B. So I'm going to list all the elements in A not, and then I'm going to list all the elements in B, and I won't list the repeats more than once. So Friday, Sunday, and Saturday. So Friday, Saturday, Sunday, Sunday, Saturday. So my answer here would be Friday, Sunday, and Saturday. Or Friday, Saturday, Sunday. Whatever order you enter it in, you should be fine. A modern deck of cards contains 52 cards. So as we get through this chapter, and then in chapter 3 we'll talk about probability, we'll do a lot with cards. So know that there's 52, 13 in each suit. We call face cards Jack, Queen, King, and picture cards are Jack, Queen, King, and Ace. And then we have cards labeled 2 through 10. So 13 in each suit. There's 4 suits: diamonds, hearts, spades, clubs. And so now we want to say how many cards are going to be in the union. How many face cards or spades are there? And we have to be careful because we're not going to count the repeats. So face cards, we know there's 4 face cards in each suit, right? So 4 plus 4 plus 4 plus 4. So there's 4 face cards. Oh, sorry, there's only 3 face cards. Right? Jack, Queen, and King are face cards. So face cards, there's 3 in each suit. So there's 3 for diamonds, 3 for hearts, 3 for spades, and 3 for clubs. And there's 13 spades, right? 13 of each suit. So this would be the number of cards that are face cards. This would be the number of spades, but I need to subtract the number of face cards that are spades. So these are 3. So number of face cards. This would be the number of spades. And this would be the repeats. Oh, sorry, there's an A in this. My pen's, see where I'm at. Okay, so the number of repeats. So what that means mathematically is, let's call this set A being face cards, B being spades. The number of elements in A union B, because that means or, would be the number of elements in A plus the number of elements in B, plus the number of elements in B minus the number of elements in A intersection B. And those are going to be the repeats. So this example, we're using and. So we're really only focusing on the repeats. So here we're looking for the repeats. how many face cards are spades. So how many face cards? I want to know how many of the cards are face cards and spades at the same time. And then we know that is 3 from the previous example. There's 3 face cards that are spades. So hopefully this helps explain what's going on in 2.1. And let me know if you have any specific questions, and hopefully I can do a video over those and post those in the question blog for Miss Van Ryan. Good luck for this week.